Hi and welcome to another lesson in the physics video series. Today we're going to be studying elastic collisions using momentum and impulse relationships. In the previous videos we studied inelastic collisions when two bodies interact, collide, and lock together and move away together. But now we're going to look at the interaction of the two-body collision problem without locking together. And that's what makes it an elastic collision. We're going to take a look at some problems where the bodies in motion are coming from different directions and impact each other. Alright, let's get started. Let's take a look at this first problem. A 6 kilogram block slides to the east across a horizontal frictionless surface with a momentum of 30 kilogram meters per second. It strikes an obstacle. The obstacle exerts an impulse of 10 Newton seconds to the west on the block. The speed of the block after the collision is. Alright, so we're going to need to use J equals F delta T equals M delta V equals P expression, which is number 14. We have to solve this problem in parts. First, we have to find the velocity before the collision, and then we can find the velocity after the collision. Let's see. The velocity before the collision is equal to the momentum for the collision divided by that mass of 6 kilograms. That gives you 5 meters per second. Now after the collision, we know that F times T, force time, equals momentum. And momentum is M delta V. And we're going to need to find the change of speed. So 10 Newton seconds equals mass delta V, because the impulse was given as 10 Newton seconds. When we divide 10 Newton seconds by the mass of 6 kilograms of that car, we now have the change of speed, which works out to be 1.7 seconds. So the rebound speed of 5 meters per second east minus the change of speed west gives you 3.3 meters per second east. And the final answer, the speed, is 3.3 meters per second. East is important because that's a positive value. So in summary, you need to find the speed of the block after the collision. We had to do a two-step process. We had to first find the incoming speed, then we had to find the change of speed from that, and then we were able to subtract to find the speed of the rebound. Alright, let's take a look at another one. Here in problem 16, we have the classic circus cannon. At the circus, a 100 kilogram clown is fired at 15 meters per second from a 500 kilogram cannon. What is the recoil speed of the cannon? What we have here is an elastic collision. So if we were to solve this problem, we have a two-body problem, a person and a cannon. That's mass 1 and that's mass 2. Each one of these masses is at rest before the explosion. Let me show you something in the derivation. Before the explosion, both masses, M1 and M2, are at rest. So V1 and V2 equals 0. So the left side of this equation is equal to 0. And then after the explosion, both masses now have a certain speed. So if the left side of this equation is 0, then this equation turns out to be M1V2 equals M2V2. And really there's a negative in there because you're moving in opposite directions. Let's go back to the problem. So when the explosion happens, both masses go into motion. M1V1 equals negative M2V2. And the way it's organized here, they have the clown on the left, they have the cannon on the right. Mass of the clown, speed of the clown, mass of the cannon, the unknown recoil speed of the cannon. And then we just simply solve 100 kilograms times 15 meters per second divided by 500 kilograms. And that gives us 3 meters per second. That is an elastic collision because momentum and kinetic energy are conserved. In this next problem, the diagram shows an 8 kilogram cart moving to the right at 4 meters per second, about to make a head-on collision with a 4 kilogram cart moving to the left at 6 meters per second. You'll notice right away that I put a positive 4 meters per second for the 8 kilogram cart and a negative 6 meters per second for the 4 kilogram cart. The direction matters. After the collision, the 4 kilogram cart moves to the right at 3 meters per second, what is the velocity of the 8 kilogram cart after the collision? So you can see that this is another elastic collision problem. The carts do not stick together, but they bounce off each other. Let's take a look at the solution as we apply the conservation of momentum expression. m1v1 plus m2v2 before the collision equals m1v1 prime plus m2v2 prime after the collision. This is a very easy problem once you understand that momentum before equals momentum after, and that the velocities are positive 4 and negative 6 respectively. So the m1 and the m2 on both sides of this equation are the same number, 8 kilograms and 4 kilograms. And the velocity before is positive 4 meters per second and negative 6 meters per second. Then when you read the problem and you see the velocity after the collision for the V2, 4 kilogram mass bounces off at 3 meters per second and moves to the right. That's a positive value. What is this V1 prime? So what does the 8 kilogram cart do? Well, we put all these numbers in the expression and we solve, and we get a final velocity of the 8 kilogram cart at negative 0.5 meters per second. Negative means moving to the left. It's that simple. Let's take a look at another one. Here in this problem, a 1.2 kilogram block and a 1.8 kilogram block are initially at rest on a frictionless horizontal surface. When compressed spring between the block is released, the 1.8 kilogram block moves to the right at 2 meters per second as shown. What is the speed of the 1.2 kilogram block after the spring is released? So this is exactly like the clown and the cannon problem. The only difference is a spring is separating the two masses as opposed to some explosion inside the cannon. So we're going to start using equation 13, momentum before equals momentum after. We can see that m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. And we know that both masses, m1 and m2, are at rest before the explosion. So this whole left side cancels out, leaving you with m1v1 prime equals m2v2 prime. And of course you have a negative because the negative indicates that one of the velocities is opposite direction to the other one. Putting in the values that we have, we could solve for the unknown. This case is v1 prime, the 1.2 kilogram. And when we solve, we get 3 meters per second to the left. Now when they say what is the speed, they don't care about the direction. They don't care about left or right. But you should know, because they could say what is the velocity, and they can give you 3 meters per second to the right or 3 meters per second to the left, and then it would really make a difference because you are moving to the left as this arrow shows us, and that's why you actually have a negative value. The negative implies direction and the value implies the speed. So there you have it. These were the conservation of momentum expressions applied to the elastic collision. Here we saw that two-body problem has either two objects starting from rest and exploding away from each other, or we had two objects colliding together and bouncing off of each other. Either way, momentum before equaled momentum after. I hope you enjoyed this video and thank you for watching. We'll see you in the next video.